What would happen if the meteorite that caused the mass extinction hit the Mariana Trench? Alright, let's set up the Chicxulub impact on the Mariana Trench. Wow, at the moment of impact, it releases energy equivalent to 3 trillion Hiroshima atomic bombs. The impact zone looks worse than my grandma's homemade apple pie, completely dreadful. The 11-kilometer deep seawater offers no cushion, and the seawater within a 1,000-kilometer radius instantly turns into plasma, forming an 800-kilometer wide, liquid scar. The initial height of the tsunami waves generated by the impact can reach 500 meters. They will hit the Japanese archipelago in 6 hours, and destroy all Pacific coastal cities like Los Angeles and Sydney within 24 hours. Even after the aftershocks travel around the Earth, they still maintain a height of 5 to 10 meters. At the same time, 300 trillion tons of dust are thrown into the stratosphere. The amount of sunlight reaching the Earth's surface drops sharply to 0.03% of its normal level. Large-scale plant death leads to the collapse of the food chain. Oh, that's not good. The impact momentum also causes a 12.7-degree shift in Earth's axis, shortening the Earth's rotation period by 1.8 hours. All 327 active volcanoes around the Pacific Ocean are activated, and the supervolcanic ash columns further worsen climate deterioration. Well, only tardigrades in the Antarctic ice sheet and tube worms near deep-sea hydrothermal vents might survive through extreme adaptation. Complex life would take hundreds of millions of years to recover, far longer than the 10-million-year recovery period after the Chicxulub impact 66 million years ago. What if the meteor that caused the mass extinction hit the moon instead? Alright, let's just have the Chicxulub meteor hit the moon this time. Whoa, the energy released at the moment of impact would be equivalent to 1 million times the total energy of all nuclear weapons on Earth. It would instantly melt rock several kilometers thick, forming a complex impact crater over 200 kilometers in diameter, similar to the moon's Copernicus crater, and also similar to my grandma's homemade apple pie. At the same time, it would hurl trillions of tons of lunar rock into space at speeds exceeding the lunar escape velocity, creating a massive cloud of debris. Hey, that's actually kind of interesting. Surprisingly, this debris would have only a limited impact on Earth, with the survival rate of life remaining above 90%. Only about 5% to 10% of the fragments would be captured by Earth's gravity. Small fragments would form a global meteor shower, while fragments larger than 10 meters would only trigger local impacts with the equivalent force of a megaton-scale nuclear bomb. 10 trillion tons of dust would enter Earth's stratosphere, but it would only reflect 5% to 10% of solar radiation, causing a global average temperature drop of 1 to 2 degrees Celsius for a few years. This is far milder than the 6 to 10 degrees Celsius cooling that occurred when the meteor hit Earth, and it would not disrupt global photosynthesis. Well, the stability of the Earth-Moon system would also remain unshaken. The Moon would stay in its orbit 384,000 kilometers from Earth, maintaining its tidal-locked state. Earth's ocean tides and climate regulation functions would remain largely unaffected. If this meteor had hit the Moon during the age of the dinosaurs, large creatures like dinosaurs would not have gone extinct, and the rise of mammals would have been delayed. Life could have avoided a global ecological collapse by migrating or evolving to adapt. Let the Earth's mass increase, and then make Jupiter a satellite of the Earth. Alright, for Jupiter to orbit the Earth stably, the Earth's mass must be far greater than Jupiter's. Generally speaking, the mass of the central celestial body needs to be at least 10 to 20 times that of its satellite to form a relatively stable system. Okay, so we'll increase the Earth's mass to 20 times that of Jupiter. Wow, the Earth's appearance changes in an instant. Oceans, mountains, and continents we're familiar with vanish in the blink of an eye, crushed into its scorching, high-pressure core. At this point, the Earth looks like a brown dwarf. Its interior may undergo mild deuterium fusion due to extreme pressure, but not enough to become a true star. Next, we'll replace the Moon with Jupiter. Despite its enormous size, Jupiter is now just a satellite. It will orbit the super-Earth along the Moon's original orbit. Orbiting each other at such a close distance, the surface temperature of both planets reaches as high as 500 degrees Celsius. Well, the super-Earth's massive gravity will exert a noticeable gravitational tug on the Sun, causing the Sun to also move slightly around the barycenter of this new Earth-Jupiter system. The orbits of the solar system begin to destabilize, and the total mass distribution of the solar system undergoes a drastic change. The sudden appearance of a celestial body with a mass close to that of a brown dwarf in the inner solar system will severely disrupt the orbits of all planets. Mercury, Venus, and Mars in the inner solar system could be flung out of the solar system by the super-Earth's gravity, crash into the Sun, or be captured and swallowed by the super-Earth. For Saturn, Uranus, and Neptune in the outer solar system, their orbits will become extremely unstable. They might be ejected into deeper interstellar space, or enter highly eccentric elliptical orbits and collide with other celestial bodies. Let Saturn collide with Saturn. Alright, let these two planets with their straw hats come into close contact. First, before the collision, their ring systems will bear the brunt. Ice and rock fragments will either crash directly into the Saturns or be scattered, forming a chaotic disk of dust. Wow, in the instant of collision, their hydrogen-helium atmospheres will form a plasma cloud under the high-speed impact. The energy released will be equivalent to 1 quintillion Hiroshima atomic bombs. A blinding light will engulf the entire solar system, creating shockwaves and interstellar clouds spanning billions of kilometers. As for their 20,000 to 30,000 kilometer wide rock ice cores, after the collision, they won't shatter under extreme heat and pressure. Instead, they'll merge into a single supercore. The ring systems, mixed with debris ejected from the impact, will split. Part will be captured by this new planet, while the rest drifts toward the inner solar system and the depths of space. Well, this collision will stir up the entire solar system. The orbits of Jupiter and Uranus will shift due to gravitational disturbances. Celestial bodies in the Kuiper belt and asteroid belt will have disrupted orbits. Ejected material pushed toward the inner solar system will form a super asteroid belt around the Sun. For thousands of years afterward, Earth will be constantly exposed to a hail of cosmic debris. Once the chaos subsides, a long rebirth begins. For the first tens of thousands of years, only a massive, scorching, and chaotic nebula will float there. But gravity, the most patient artist of all, will step in again. It will slowly gather the scattered material, eventually forging an entirely new king of planets. A behemoth twice the mass of Saturn, spinning rapidly, and possibly even more oblate in shape. What would happen if we removed all other planets in the solar system, leaving only Earth? Okay, let's make it happen. Neptune, gone. Uranus, gone. Saturn and Jupiter, gone. Wipe them all out. Once the deletion is done, let's set this system in motion. Whoa, the asteroid belt in the solar system immediately falls into a state of leaderless chaos. Under the Sun's gravity, celestial bodies in the asteroid belt and the Kuiper belt start orbiting the Sun. This drastically raises the risk of Earth being hit by asteroids. We really miss Jupiter, the big brother of the solar system. With a mass 318 times that of Earth, it acts like a massive gravitational fishing net, catching over 90% of the asteroids heading toward the inner solar system. Now, without it, there are 1 million space cannonballs. Asteroids over 1 kilometer in diameter, just in the asteroid belt. One wrong move, and they could crash into Earth, repeating the extinction of the dinosaurs. This would trigger global wildfires, dust clouds blocking sunlight, massive plant die-offs, and broken food chains. Such impacts might occur once every decade. Well, even scarier, Earth would lose its orbital stabilizers. Originally, the gravity of planets like Saturn and Uranus acted like weights on either side of a scale, keeping Earth in a stable orbit around the Sun. But without them, Earth's orbit would be like a runaway horse, sometimes getting too close to the Sun, making the equator hot enough to fry eggs, sometimes drifting too far, causing the Arctic ice sheet to spread all the way to the Yangtze River basin. You might even leave home in a short-sleeve shirt in the morning and need a down jacket by noon. The only silver lining is that the Moon won't leave us. Its orbit is mainly maintained by Earth's gravity, with other planets having barely any impact. From now on, we can still watch the Moon's phases, and the tides by the sea will remain regular. But this small comfort won't stop the collapse of the ecosystem. Plants and animals won't have time to adapt to frequent extreme climate changes, vanishing one by one from Earth. In the end, only the microbes that can survive extreme environments, like those around deep-sea hydrothermal vents, might remain.